Hello, good afternoon. Welcome to today's class. If you're online, please say hi. All right, we are going to look at a topic called linear expansivity, which is specifically under heat energy. So I'm going to review that heat energy, then I will go deep into linear expansivity. Is that clear? All right. Ajoku, you're welcome. Kewe, you're welcome. Osakwe, you're welcome. So let's look at heat energy. Now, under the heat energy, we're going to be explaining the concept of heat and temperature, because heat leads to temperature difference. Okay. Um, I'm going to look at concept of heat and concept of temperature, so you can know the difference between heat and temperature and the effect of heat on a particular body before we move to the main topic, which is what we have today as linear expansivity. All right, so let's move into concept of heat. All right, so you can put it down. Rosemary, you're welcome. Okay, Chukwumosi, you're welcome. David, you're welcome. Please give it a thumbs up. All right, so let's look at the concept of heat. Heat is a form of energy called thermal energy. Thermal energy in the sense that it flows as a result of temperature difference. Heat flows from a hotter to a colder body, still as a result of temperature difference. Heat is a scalar quantity. Unit of heat is what? Joules. So if you're asked to state few things about heat, you can say a little thing about heat. So let's go into temperature. All right. So looking at the concept of temperature, we can define temperature as the degree of hotness or coldness of the body. It is a scalar quantity. The unit of temperature is what? Kelvin. Unit of temperature is Kelvin. Now we can actually distinguish between the concept of heat and what? Temperature. So now when we apply heat to a body, it has so many effects on a body. So that leads us what to say to be effects of heat. What are the effects of heat on a particular body? So put it down, let's proceed. Alaba Prive, you're welcome. Ajoku, is it clear now? Please check your network if it's clear now. Rosemary, check your network, okay? You can check your network. Robinson, yes, this is today's class. We just started. Rosemary. Rosemary, I did not see you yesterday. Olachi Ajok, I did not see you yesterday. All right, is it clearer now? Okay. David, I did not see you yesterday. Yale Dem, good morning, you're welcome. Okay, Yala Esther, you're welcome. How are you? Osakwe Peace, you're welcome. Thank you so much for coming, ma. Please copy what we have on the board. Yala Esther, I didn't see you yesterday. Okay, no problem. Now, are we done? Want to proceed to another thing? Are we done writing? Okay, so you were present yesterday. Okay. All right. So let's move into the effect of heat. Effect of heat on a body. Effect of heat on a body. All right, so let's take the effect of heat. All right, so these are the effects of heat on a body. The first one is change of state of the body, change in temperature of the body, expansion of the body, thermionic emission, chemical change, changes in pressure, and change in the physical properties of the body. I'm going to be explaining them one after the other. If we say change of state of the body, for example, if you bring a solid, for example, a plastic, bring a plastic, when you apply heat to it, it's going to change its state. It's going to change its state from being a plastic, which is also a solid, to melting point, or to melt, which will be a liquid. Now another example is this: if you bring your ice block, which is also a solid, or bring your soup or your stew from the freezer, which is a solid, by the time you apply heat to it, it's going to melt and change to what? Liquid. So that is the change of state. The state will change from solid to what? To liquid. Now if you also apply heat, remember that food, that soup you actually brought out from the freezer was in its solid state, okay? Then the temperature of it was very low. By the time you apply heat, the temperature will do what? Will rise. So that is the change in temperature of the body, that making the body to change from solid to what? Liquid state. Now expansion, when you bring that plastic and you apply heat to it, it's going to do what? Melt. And the body is going to expand, just like hitting a uh, plastic bucket or plastic rubber. Is going to melt and do what? Expand. And once it melts, it will expand. That is what we mean by expansion of the body. Now thermionic emission is the process of emission of electron from the surface of a hot metal when they are being heated. Now when a hot metal is heated, how do I mean? If you get a boiling ring and plug it, connect it to a socket, once the switch is on, you're going to experience what? Streams of electron moving up from the surface of that ring, a boiling ring, especially that ring end. That is what we call thermionic emission. Once that is connected, there will be an emission from the surface of the hot metal. That is what is said to be thermionic what? Emission. Then chemical change. Chemical change means when you get a piece of paper or a log of wood, you burn it, is going to change to what? To ashes. That is chemical change. We all know in chemistry that in chemical change, he said a new substance is formed and it is not easily reversible. So that new substance is formed is going to be the ashes which is produced from the log of wood that was being burnt. I don't know if you get it. So that chemical change, the object has changed from each state to another state, and it is not easily what? Reversible, because that ashes cannot reverse back to the log of wood. So that is still part of the effect of heat on a particular body. Then the next is changes in what? In pressure. Now when you apply heat to a particular, for example, you want to cook your beans or your rice, you are going to apply pressure by apply heat. Heat will increase the what? The boiling point, which is going to increase the pressure. That causes the changes in what? Pressure. Now change in the physical properties of the body. Certain the physical properties of the body will change because of heat has been applied to what? It. For example, as you refer to this chemical change, once that object is burnt, that example I did the log of wood, once the log of wood is burnt to ashes, the chemical properties has, the physical properties has been what? Has been changed. Before it was a log of wood, now it now came out to be what? Ashes. Now it's because of the effect of heat on that particular body that made that object to be in that manner. I hope that is clear. So you should know all these effects of heat on a body. One is the change of state of the body, the change in temperature of the body, thermionic emission, expansion of the body, chemical change, changes in pressure, and also the change in the physical properties of the body. I hope that is clear. All right, you can put it down. Let's dive into what we have today, which is linear expansivity. Or if you are just joining us, give it a thumbs up. Give it a thumbs up, okay? Double tap on your screen. If you are done, please let me know. Let's proceed to the next one. I want the class to be interactive, okay? Let me be sure you are following me. All right, let's proceed. All right. So the one thing I'm going to look at now is thermal expansion. So what is expansion? Expansion is the increase in size of an object. In as much as heat is applied to a particular object, it must do what? Expand. Once heat is applied to an object, it must do what? Expand. Now if you have a solid, this is a solid, okay? So if this solid increase only by the length, it is called what? Linear expansion or expansivity. If the solid expand by the what? The length and the breadth, it is called what? Area expansivity or expansion. If it increase the length, breadth, and height, it is called what? Volume what? Expansion or expansivity. What am I trying to say? I mean that expansivity involves the parts of the object that is increased. If the increase in the size is only by the length, it is tagged as linear expansivity. But if the increase is it is tagged what? Area expansivity. But if the increase in the size is only by the length, breadth, and height, it is tagged to be what? Volume expansivity. I don't know if you get it. So we are going to be looking at the linear expansivity right now. Linear expansivity, that is the increase in the length. So the question is, what is linear expansivity? So let's proceed. Please, if you find it difficult, you can. If I'm too fast, you can let me know. So this class, I want it to be interactive, okay? Yes, Christiana, you're welcome. This today's class, we just started. All right. The first thing we're going to look at linear expansivity. Anywhere you see linear expansivity in physics, the symbol means what? Alpha. The symbol means what? Alpha is defined as the increase in length per unit length per degree rise in temperature. Is that clear? Linear expansivity is defined as the increase in length per unit length per degree rise in temperature. The increase in length per unit length per degree rise in temperature. I want you to pay attention to this particular topic. Now, anywhere you see linear expansivity, the symbol is what? Alpha. So this alpha is increase in length divided by what? Original length multiplied by temperature rise. Okay? Now, how do I mean by increase in length? For example, I told you once heat is applied to a particular object, it's going to increase in each side. This is a marker. If I this we can measure the length of this marker right now. For example, the length is 5 centimeters. So that becomes my original length before heating. I will say 5 centimeters. Right? By the time I apply heat to it, it's going to expand. And once it expands, the length is not going to remain the same. Okay? I'm going to get a new length. I may have like 6 centimeter or 6.5 centimeter. Let me say my L2 is 6.5 centimeter. Do you understand? So looking at it, there is an increase in length. There's an increase in the length. So because of the heat applied to it, now the increase in length becomes the L2 minus what? The L1. I don't know if you understand what I just explained. That for you to get this increase in length, the object has increased more than its original size. Now, if, for example, before we heated this marker, the length happens to be 5 centimeters. Now, after heating, we now observe that the thing has increased in its size and it became 6.5 centimeters. Now, what is the increase in length? For you to get the increase in length, that is 6.5 centimeters minus 5 centimeters. Is that clear? So the increase in length becomes L2 minus what? L1. Is that clear? I hope you're not confused. All right. So we can say that alpha, which happens to be linear expansivity, is equal to what? L2 minus L1 all over the original length is what? L1, and the temperature rise becomes theta 2 minus theta 1. Why do we have theta 2 minus theta 1? Before we started heating that solid, it already have an initial temperature. Right. By the time you are done heating it, the temperature will increase and the length will increase also. So that gives us the right to temperature difference. Now, this temperature difference is such a whereby you have already gotten the difference between the initial temperature and the final temperature. Is that okay? So this is the formula for linear expansivity. I'm going to be explaining it more so I can understand better. All right, put it down. Thank you so much, Neki, for coming. I really appreciate. Please give it a thumbs up. Christiana, I say you don't understand. Please tell me what you don't understand. I just finished explaining. Please tell me what you don't understand. Christiana, I'm waiting. Let's proceed. All right. So, Christian, let me go back to explain it again. All right, I said that linear expansivity, that the symbol is alpha and is defined as the increase in length per unit length per degree rise in temperature. So once you see alpha in physics, it means linear expansivity. Is that clear? All right, so from the definition, it means that alpha is equals to the increase in length. Once you hear per unit length, that means that is over original length, then per degree rise in temperature equally multiplied by temperature rise. Now, I was explaining this increase in length. I said, what do you mean by increase in length? For example, I want to heat this marker. Now, first, I have to check the length of this marker and the temperature before heating it. Is that clear? Now, if I check the length of this marker and the temperature, the length of the marker becomes L1. For example, it happens to be 5 centimeters. I have to record it as 5 centimeters as my original length before heating. Now, my initial temperature becomes theta what? Theta 1. Is that clear? Now, after heating this marker for a very long time, I decided to say, okay, let me check how it has expanded. I now realize that the increase in size, that the length of the side, that the length of this marker has increased in each size. Okay, so I went ahead to record the new length. That becomes my L2. Okay, so by the time I find the difference between the L2 and L1, that will give me the increase in length. So that is what I mean by increase in length. Is that clear? All right. Now that increase in length becomes L2 minus what? L1. So that is the formula for the up. I have it here. Then divided by the original length is L2, and the temperature difference or temperature rise becomes theta 2 minus what? Theta 1. Is that clear? All right, I want to do a review again on the explanation of this linear expansivity so that I can understand better. Put it down fast. Let's proceed. Now, I believe we can proceed now. All right. Now, alpha, we all know that alpha in physics is linear expansivity. So we can say that alpha is L2 minus L1 all over L1 bracket theta 2 minus theta 1. Right? Now, this formula is when you're looking for linear expansivity. When you're looking for linear expansivity. For example, you may be asked to find the new length, to calculate the new length. Now, new length is your L2. You don't need to start solving to make L2 the subject. We are going to generate a formula that we are going to use to solve for new length. Now, this one alone is for what? Linear expansivity. Okay? Now, you're asked to calculate for new length. I'll just write for new length. And new length is what? L2. If I ask to calculate the new length, how do we do that? We can do that by making L2 the subject. So let's work it out. Alpha is equals to L2 minus L1 all over L1 theta. If I say L1 theta, remember that theta is the same thing as this. This is when you find the difference between the two temperatures, they're going to be tagged as theta. Okay? For example, you're given a temperature rise, that is one temperature, you're going to use it as theta. But if you are given two temperature difference, you're going to find the difference to use it as 2 theta. So don't get it confused. Now, I want to make L2 the subject, so what do? I'll say that this is over what? 1. I'll do cross what? Multiply by saying L2 minus L1, this multiplied by this, I'm going to have L1 theta what? Alpha. Is that clear? Now I'm carrying this L1 to this other side because I want to make L2 the subject, which is my new length. So I have L2 is equals to L1, this one cross over to be plus L1 theta alpha. Is that clear? All right. What is common? Something is common, which is what? L1. So I'm going to have L1 bracket. 1 will remain here because if I bring out this from the, if I put it, bring this out, L1 out, what will remain here is 1. I'll have 1 plus theta alpha. Is that okay? So this formula is what you are going to use to solve for our what? For our new length. Hope that is clear. You're going to use this formula to solve for our new length. The only thing you can ask to find, maybe ask to find the linear expansivity, which is alpha, or you ask to find the new length, which is L2, or you ask to find the change in length. So let's go to the change in length. Now, you can call it change in length or increase in length or expansion or safety gap. All these things I'm saying, it meant just one thing, just one. But I'm using all of them to show you the language the examiner can change, just to ask you a particular question. They can ask you to find the increase in length, or they can say the change in length, or they can say the expansion, or they can say the safety gap. They all mean the same thing. So we want to get it from that formula too, by saying alpha is equals to L2 minus L1 all over L1 theta. Is that clear? Now what you are going to do, because the whole of this is the increase in length or the change in length or the linear expansion or the safety gap. Now I want to make it the subject simply by saying this is over 1 cross what? Multiply. So what do we have? We have that L2 minus L1 is equal to L1 theta what? Alpha. Now see what you are looking for. L2 minus L1 is the increase in length, is the change in length, the thermal expansion, is the safety gap. Is equals to L1 multiplied by temperature rise multiplied by linear expansivity. Do we understand? All right. We still have another method of doing that. This is a short method of finding the increase in length. But another long method is by once you already have your original length, you are going to use this formula to get your new length. Then you subtract for whatever thing you have from the original to get this increase in length, of which these three things multiplied together is going to give us the same as what we just did. So we are going to look at it and solve few problems. I hope that is clear. Put it down, please. All that you don't understand, tell me what you don't understand. Yes, I'm waiting. Tell me what you don't understand. All right. So I can tag here L1 is original length, L2 is new length, theta is temperature difference. Okay, alpha is linear expansivity. All right, Christina, the theta is temperature difference. As if you're given two different temperatures, you can find their difference. Is that clear now? Please, I need your response so I can know whether you're following me or not. All right. Kewe, you're good, okay? Alabo, is that cleared? Christiana, is it cleared? Robbins, is it cleared? What is it cleared? Do you understand? Rosemary, is it cleared? Ajoku, do you understand? Davida, do you understand? Yala Esther, do you understand? Okay. Esther, you don't need to find the formula for L2 after OPR. Esther, you don't need to find the formula for L2. Just get the formula for L2. That is why I've derived it for you. So you're going to use it to solve your problem. OPR, where is OPR? After OPR. Is it expansion or safety gap? Expansion or safety gap? Linear expansivity, temperature difference? Okay, is that what you mean? After R. Where do we have R? There's no R here. Is it increase in length, change in length or increase in length, or expansion or safety gap? Which one? Change in length or increase in length, or expansion or safety gap? Okay. So that is what I have. All right, should we proceed with question solving? Because we need to solve a lot of work today. Okay, I've said it, change in length or increase in length or expansion or safety gap. Is that clear? Change in length or increase in length or expansion or safety gap. Most, is that clear? Okay, Christina, I told you to chat me up on WhatsApp that will add you. Vijaya, thank you so much for coming. I'm very well, thank you. Thank you for coming. All right, please, can we take down the question on the board so that we can solve it? So you understand how we can solve that problem. Okay, what happened to the board? Can you see now? Is it clearer now? Davida, Kewe, is the board clearer now? All right. Are you done writing the question? Please, are we done writing the question? All right, so let's proceed. Okay, let's solve. A copper rod whose length at 30 degrees Celsius is 10.0 meters. A copper rod whose length at 30 degrees Celsius is 10. Find its new length, then take for copper as 0.000017 per Kelvin. Looking at this question, the first thing that will come to our mind is to state our parameters. A copper rod whose length at, this is my initial temperature, so that is my theta 1, is given as 30 degrees Celsius. Okay, that the length is what? 10.0 meters. That is L1. Is that clear? Now it's heated to 50 degrees Celsius. That becomes my final temperature. Okay, find its new length. We are looking for L2. All right, and we are asked to take the alpha for copper to be 0.000017 per Kelvin. Right, now before I solve, because I'm looking for L2, I must tell you how the units of alpha became per Kelvin. From the definition, alpha is equals to L2 over L1 all over L1 theta, right? Now what's the unit? This is length. Length is measured in meters. Okay, divided by, this is also length measured in meters, and temperature is measured in Kelvin. Is that clear? Now this meter is going to cancel meter, so unit of alpha is 1 over what? K. Is that clear? But because we don't always want our unit to be in form of a fraction, so it's going to be in a numerator, so I'm going to carry this K up, so the unit becomes per Kelvin. Okay, so that is why the units of alpha, which is linear expansivity, is per Kelvin, and that is what we have here. Are we cleared? Do we have questions before we proceed? Kewe, Esther, Wosu, Rosemary, are we cleared? Do we understand? Before I proceed with the solving, do you understand why the unit of alpha is per Kelvin? David, I say you don't understand what? David, I don't understand what? Please be active. Let me know so we can proceed. All right. Now let's solve. I've already given you the unit, the formula for L2. L2 is equals to L1 bracket 1 plus theta alpha. Is that clear? L2 is equals to L1 bracket 1 plus theta alpha. Now, for us to be able to solve that, what you are going to do, let us find theta. And what is my theta? Theta is my temperature difference. Now I have two different temperatures. I'm going to solve it out to get my temperature rise. That is theta 2 minus theta 1. 50 minus 30, the answer becomes 20 degrees Celsius. And the question is, I thought the unit of alpha is Kelvin. How come this temperature is in degrees Celsius? Now, the answer to this question is, if you convert this to 27 to Kelvin by adding 273, and also convert 30 to Kelvin by adding 273, by the time you subtract it, the difference is going to give you what? 20 Kelvin or 30 degrees Celsius. Do you understand? So it does not really have effects on the temperature. So whatever temperature given to you, you can work with that without conversion. It does not really have effect. So my theta here becomes 20. So let me go. L2 is equals, what's my L1? 10 bracket 1 plus my theta is what? 20 multiplied by my alpha is 0.00017. Is that clear? All right. L2 is equals to, there is a particular thing you must note, that this is a multiplication sign connecting the theta and the alpha, which is this and this. So don't say 20 plus 1, you are wrong, because you are going to work them out with it. I hope I'm clear. Now you're going to work them out before adding plus 1. So with your calculator, going by that, I have 20 multiplied by 0.00017. So what am I going to have? I'll bring down this one plus 3.4 times 10 raised to the power of minus 4, right? I'm going to teach you how to press this with your calculator. That's if you have your calculator right now. Now, once you are done with that, you can now say plus 1. Okay? Then it's going to give you 1.0034, right? Now, whatever so you have, you can now multiply by 10. By saying multiply by 10, and the answer becomes L2 is equals to 10.0034 meters. Is that clear? Do you understand? Now, the first thing is to analyze your question and bring out your parameters, and I went ahead to find the temperature rise, which is saying theta 2 minus theta 1, right? For example, if you are given just a particular temperature, which is temperature rise, you don't need to subtract it, just use that particular temperature straight. Now, for us to get the new length, you just have to use our formula straight by saying L2 is equals to L1 bracket 1 plus theta alpha. Is that clear? Now, what's my L1? In the question, I'm giving L1 to be 10.0 meters. Now, put bracket 1 plus my theta is 20, while my alpha is this. I put in my value. Now, the next thing to do is to note that this is a multiplication sign between this and this. So what you're going to do is to multiply it first before adding plus what? 1. Do you understand? If you don't do that, if you say 20 plus 1 before you multiply, you are wrong, because you have to work it out based on the way it is in the formula. All right? So we're going to have 3.4 times 10 raised to the power minus 4, right? Whatever thing you have, you can now add plus what? 1. And the answer becomes 1.00034, right? Before I now open the bracket to multiply by 10. And my final answer becomes 10.0034 meters. Is that clear? All right, put it down. Please, do you understand? David, can you see it now? All right. Esther, you understand, okay? Christiana, you understand, okay? All right, let's go to another example. Okay, wait, are we still here? Do you understand? Let's look at another example. Okay, you say you don't understand how I got 3.4. Now see what I did. I told you that my theta is 20, my alpha is this, right? I just use my calculator to multiply 20 multiplied by 0.000017. It's going to give me 3.4. Okay, then look at it, there is a power up. You're going to see multiplied by 10 power minus 4. Is that clear? All right, then I simply want how I got this. I'll now add 1 to get this. I'll now multiply by 10 to get this. Yes, that's what I just did. All right, so let's look at another example. All right, so put it down. Let's solve. Davida, will you still find L1? No, L1 is already given. Okay, you're using L1 to find L2. You're looking for new length, which is L2. All right, take down the question on the board. Let's solve. All right, are we done writing? So let's solve together. A metal of length 15.01 meters is heated until its temperature rises by 60 degrees Celsius. If its new length is 15.01 meters, calculate its linear expansivity. Let me go again. A metal of length 15.01 meters is heated until its temperature rises by 60 degrees Celsius. If its new length is 15.05 meters, calculate its linear expansivity. Now let's go. Now, a metal of length, this is the L1. The first length given to you is the L1, except they say it is increased in length. So this is the original length before heating. I have 15.01 meters, right? It's heated until its temperature rises by 60 degrees Celsius. So the temperature rise is 60 degrees Celsius, right? If its new length is 15.05, that's my L2 is 15.05 meters. Calculate its linear expansivity. That is, we are looking for what? Alpha. Is that clear? Now, what do we do now? We are certainly going to use our formula, which is alpha is equals to L2 minus L1 all over L1 theta. Is that clear? Now we only have temperature rise, which is only one temperature. You don't need to subtract, you're just going to work with it that way. All right? So let's go. We say alpha is equals to, what's my L2? My L2 is 15.05 minus my L1 is 15.01. Are we clear? All right? Please don't get confused. Divided by my L1 is what? 15.01 multiplied by 60. Do you understand? So we're going to use our calculator to subtract 15.05 minus 15.01 is going to give me 0.04. Okay? Then let's multiply these two together. 15.01 multiplied by 60 is going to give me 900.6. Okay? Now let's divide. So we have 0.04 divided by 900.6, and my answer is 4.44 times 10 raised to the power of what? Minus 5 per Kelvin. So that is my answer to this question. Is that clear? After setting the parameters, I will state my formula, and I'm looking for alpha. Remember the previous one, we looked for linear new length. Now we are looking for alpha, and our formula is L2 minus L1 all over L1 theta, right? Now, this is substituting what we have. My L2 is 15.05 minus 15.01, okay? Divided by my L1 is 15.01 multiplied by 60. By the time you subtract this, you're going to get 0.04. All right, then after dividing, I got my answer to be 4.44 exponent or power minus 5 per Kelvin. Is that clear? All right, put it down. All right, please, are we cleared? Kebe, do you understand? David, do you understand? Okay, Chiku, do you understand? Okay, Chimoso, do you understand? Christiana, do you understand? All right. Are we together? Do you understand? All right, do we understand? Let's go to the last one for today, because we'll soon end the class. If you are just joining us, give it a thumbs up and make sure you subscribe to this channel. Christian, I told you to send me a WhatsApp message so I can add you to the group. Or any of your class members can add you to the group, okay? I'll just approve. Any of them can add you, I will approve. All right, let's move to the last one for today. You write the answer straight, is it correct? You have to show your workings. The way I showed it, you have to show your workings. Except it's an OBJ question, but if it happens to be theory, you have to show us how you got. How I got meter. How you got meter. Which one is meter? There is no meter here, Davida. Okay, chat me again after this class. Chat me around. Chat me after this class. I'll respond. Okay. Just tell me that you are Christian. I will respond. Okay. All right. Let's move to the last question for today, so we can end the class. All right, Christiana, 4.44. Look at that calculator. You're going to see raised to the power up. You must include it because it means that the digit started from 0.00. It's like putting it in standard form, okay? So this is correct, but there is a power that's attached to the question. That is what I added. And without that power, this one you just gave me now is wrong. Okay? So you must add that power when you are solving yours because it's part of the answer. It means that zero started before this number. That's what it means. So when you are calculating yours, you make respect to that. Exponent minus 5. Yes. I think that is what we have there. Yes. Christina, yes, you are correct, but you're going to write it the way I wrote it, not this way. You're going to write 4.44 times 10 raised to the power of minus 5. It's the same thing as exponent minus 5. Do you understand? So scientifically, you're going to write it this way. 4.44 times 10 raised to the power of minus 5. Okay? So in your calculator, this times 10 means what? Exponent. This times 10 means exponent. Then you're going to use the smaller power enclosed in bracket. Then put 5 to get this. Do you understand? So if you had got this, you're correct. We are going to write it this way and not putting exponent minus 5. Do you understand? Right. So copy what you have on the board. All right, please copy what you have. This is the last question for today so that we can end the class. Christiana, is it clear now? Are you done writing? Okay, where are we still here? All right. All right, so let's solve this last one together so we can end the class. The question says, a metal rod of length 100 centimeters is heated through 100 degrees Celsius. Calculate the change in length of the rod. Let me go again. A metal rod of length 100 centimeters is heated through 100 degrees Celsius. Calculate the change in length of the rod. We are given the linear expansivity of the rod as 3 times 10 raised power minus 5 per Kelvin. So the first thing we are going to do is to set our parameters. And from the question, this is my first length. Now, before heating, so my L1 becomes 100 centimeters, okay? Then my temperature difference, which is temperature rise, theta, is given as 100 degree Celsius. And we are looking for the change in length. Remember, I told you that the change in length is the same thing as the increase in length, the same thing as safety gap, the same thing as expansion. So whichever language the examiner choose to use, they all mean the same thing. All right, so this is what we are looking for, L2 minus L1. That is what we are looking for, right? And we are giving alpha to be what? 3 times 10 raised to the power of minus 5 per Kelvin. Is that clear? All right, so the formula we are going to use to solve this is the formula for change in length or increase in length or expansion. That is L2 minus L1 is equals to L1 theta what? Alpha. That means you're going to multiply all through with this to get the answer. So what is my L1? My L1 is 100. My theta is equally what? 100. And my alpha is 3 times 10 raised to the power minus 5. Is that clear? Now you're going to multiply all of them together, and my answer is going to be 3 times 10 raised to the power minus 1 centimeter. Okay, so my L2 minus L1, which is the increase in length, is the same thing as saying this is 0.3 centimeters. Do we understand? Is it cleared? All right, put it down. All right, Christiana, so listen to the question. A metal rod of length 100 centimeters is heated through 100 degrees Celsius. Calculate the change in length of the rod. Calculate the change in length of the rod. And we are given the linear expansivity of rod to be 3 times 10 raised to the power of minus 5 per Kelvin. Is that clear? All right. Please put it down. Esther. Okay. Do we understand? All right, Esther, let me go back again before I end the class. A metal rod of length 100 centimeters is heated through 100 degrees Celsius. Calculate the change in length of the rod. I am given the linear expansivity as this. Before I started solving, I've already stated the formulas for each of them, so that when you have a particular question, you know the formula to use to get your answer. All right. So from this question, we are given the length to be 100. That is my L1. We are given the temperature difference to be 100. And you are looking for change in the length. That means you're looking for L2 minus L1. And from the question, we have our linear expansivity to be 3 times 10 to the power minus 5 per Kelvin. All right, so the formula we are going to use is L2 minus L1, which is what we are looking for. This is what we are looking for, okay? And it's equals to L1 theta what? Alpha. Is that clear? Now, what's my L1? My L1 is 100. That's what I have here. Multiplied by my theta is 100. Then my alpha is 3 times 10 to the power minus 5. Okay? So what I did was to just multiply all these ones. And the answer became 3 times 10 to the power minus 1 centimeters, which is the same thing as 0.3 centimeters. Is that clear, Esther? I hope you understand it now. All right. All right, David, I use calculator to do that. Or you can actually use your head. Now I can work it out. Let me work it out the way you understand. Let me solve without using calculator. Let's see if our brain is going to work together. So this is 100 times 100, same thing as saying, right? Multiply by 3 times 10 to the power what? Minus 5. Okay. Now this 1000, when you want to change the standard form, same thing as saying 1 times 10 to the power of what? 4. Okay. That is changing to standard form. I have this. They multiply by 3 times 10 to the power what? Minus 5. Do you understand? Okay, so look at, I'm going to work on this together. 1 times 3 is going to give me what? 3. Okay. Multiply by 10 raised to the power of 4 multiplied by 10 raised to the power of what? Minus 5. Is that clear? Now, working on the power with the law of indices, I have this as 3 times 10 raised to the power what? This will be 4 minus 5 because the bases are the same. I'm going to pick one of the bases and add the powers. So that will give rise to 3 times 10 raised to the power minus 1 centimeters, right? Which is the same thing as 0.3 centimeters. Okay. Yes, David, I didn't solve it like the first one because the question was not the same. Okay. We have 3 formulas for solving this based on what you are given. And I gave you 3 formulas. If you're asked to find linear expansivity, it has its own formula. If you're asked to calculate new length, it has its own formula. If you're asked to calculate the change in the length, it has its own formula. So if you go back to your notes, we are going to see the formulas I gave you. So I brought out questions based on each of them, which will help you to go back and see what the formulas have given and see how we can apply. That's what I just did. So you don't get confused when you see questions. I gave you 3 formulas and I solve problems from each of them, which will help you to understand better. Yes, Christian, I did not add one to it because I did not use the first formula to solve, okay? So like I said, I am solving the problem based on the formulas we generated or we got or we derived from the first definition. So depending on what you are looking for, you are going to solve it that way. Yes, the first I solved was for new length. If you go back to your notes, you're going to see new line. That's the first one I solved. Christiana, can I write the formula? I wrote the formula earlier before. Okay, after this class, you can watch this video. It's going to be online, so you can just go back to my channel. You're going to see this topic that we did today, linear expansivity. Go and watch it again. You're going to see the formulas when I derive the formulas, so you understand better, because I have another class now. All right, thank you for staying and sticking to the end of this class. I'm going to be dropping assignments for you in my community. So you're going to go to my channel, go to my community. You're going to see an assignment there under this particular topic, okay? So you can pick it there and answer the questions, and drop your answer in the comment section. Don't forget, if you have any question, you can ask me in the group. Is that clear? All right. So I'll see you next time tomorrow in the next one. Bye for now. Yes, Davida, you can add her, then I'll approve. All right. All right, you're welcome. See you next time tomorrow.